Welcome to TechDaily.ai, the show that really cuts through the noise. We bring you the essential insights you need to be truly well-informed. Today, we're diving deep into, well, the engine room of modern software. We're talking containers, Kubernetes, and CI/CD pipelines, that powerful trio that's fundamentally changed how we build and deliver applications. For anyone building or managing software today, these terms are just everywhere. So our mission for you, the learner, is to give you those aha moments. We want to show you not just what these technologies are, but really why they've revolutionized how applications get delivered. And just quickly, this deep dive is brought to you by Stonefly. They're your trusted solution provider and an advisor in enterprise storage, backup disaster recovery, hyperconverged solutions like VMware, Hyper-V, Proxmox clusters, AI servers, SA365, that's a turnkey security appliance, and public and private cloud. For more information on how Stonefly can support your infrastructure, just check out stonefly.com.
Absolutely. And it's quite a journey we're going to trace today. From the days of manual, often really painful software deployments to the current automated, highly scalable, cloud-native environments we see now. This isn't just about buzzwords, right? It's a story of problem solving, innovation, and it directly impacts how reliably and crucially, how quickly new features actually reach users all over the world.
Okay, so before we jump into that shiny, agile, automated world, let's maybe take a quick trip back. Can you paint a picture for us? Think back, before containers, before Kubernetes. How did applications actually make it from, say, a developer's machine into the hands of a user? And what were the biggest headaches? What were the real pain points for teams back then?
Yeah, if you go back, applications were typically installed directly onto specific servers, bare metal or maybe early VMs. And they were often deeply integrated, tangled up with the host operating system itself. So think about it. A developer would finish their code, right? And then an operations team, often completely separate, would have to manually install that software, plus all its dependencies, everything it needed, directly onto a production server. It was laborious.
Okay, I've heard stories about this, almost like legends now. The situation where maybe a developer needs a specific library version, let's call it X, for their app to run. But then another critical application sitting on that very same server needed library version X+1. How on earth did teams even navigate that kind of dependency nightmare?
Ah, yes, that was the classic dependency hell. It was a huge headache. Applications would absolutely demand specific library versions, leading to constant conflicts on any shared server. Ops teams often had to resort to these really messy workarounds, like installing both versions in different places and then trying to trick one app into using a non-standard path. It was fragile. Or maybe even worse, they'd just provision entirely separate, often really oversized virtual machines for each individual service, even if those services could have easily shared a single host's resources, all just to avoid those versioning battles. It was incredibly inefficient.
Right, so it really became the poster child for that infamous problem. Well, it works on my machine.
Yeah.
The code runs perfectly fine on the developer's laptop, but then just completely hits a wall in production.
Precisely. That inconsistency was a massive, massive issue. Deployments were complex, they took ages, and they were so prone to breaking. Why? Because the local environment and the production environment were rarely, if ever, identical, especially across different OS distributions, say different Linux versions. And sometimes configuration changes were even made directly in production, maybe a quick fix, and never documented or put into version control. So you get this unpredictable behavior, really hard to trace bugs. The thing you deployed was just the code itself, not its whole environment. This created a huge gap, a real chasm between the dev teams and the ops teams.
Wow, yeah. That paints a very clear picture of the challenges. So given all those pervasive problems, what was the first real game changer? What started to untangle this mess and pave the way for how we deliver software today?
Well, the first truly monumental step forward was containerization. Imagine taking your application, right? Along with every single thing it needs to run its code, config files, libraries, all those dependencies we talked about, and bundling it all up into one neat, self-contained, isolated package. That's essentially what a container is. It creates this fully functional and crucially, truly portable computing environment just for your application. It guarantees it will run the same way everywhere.
Okay, so it's like giving your application its own little bubble. Its own tiny, consistent world to live in, completely separated from everything else running on the same server.
That's a great way to put it. Exactly. Each container simulates a different software application, and it runs its processes in complete isolation from others. But here's where it gets really fascinating and efficient. While they are isolated, multiple containers running on a single host machine can still share the underlying operating system kernel. This makes them significantly more lightweight, much more resource efficient than traditional virtual machines. VMs each need their own full, separate operating system. Containers don't. It's efficiency, but at scale.
And I know Docker played just a massive role in bringing this tech to the mainstream, made it accessible. What were the key advantages Docker introduced that really pushed containerization forward?
Docker really did make containerization practical for everyday developers. Its number one advantage has to be cross-platform consistency. A container built on a developer's laptop, for instance, will run identically on a testing server or in staging or in production. It doesn't matter if the underlying OS is slightly different. This consistency dramatically reduces that deployment panic we used to see. Containers are also incredibly memory and storage efficient. Like I said, no full OS overhead for each one. And critically, Docker enabled high-speed build and deployment. Developers could automate so much of the packaging process. And because Docker images are built in layers representing incremental changes, builds became much, much faster. This naturally supports continuous integration. Ultimately, this delivered remarkable flexibility and scalability. Developers could use pretty much any language or framework they wanted and easily scale resources up or down.
Okay, so containers, undeniably, they solve that it works on my machine issue, and they make applications wonderfully portable. But what happens when you're suddenly dealing with hundreds, maybe even thousands, of these self-contained applications? Doesn't that simplicity kind of give way to a whole new kind of complexity? Managing all of that? That sounds like an overwhelming task in itself.
You've hit on the next big question exactly. How do you manage, orchestrate, and scale all those containers efficiently when you have so many? That's precisely where container orchestration steps into the picture. And the undisputed leader, the standard, really, in this incredibly vital space is Kubernetes.
Kubernetes, right. That name is everywhere now. It's gone from being sort of a niche Google project to being practically synonymous with modern cloud infrastructure. For listeners trying to wrap their heads around it, why has it become so central? What exactly does Kubernetes do?
Well, Kubernetes is an open source system. It originally came out of Google, as you said, and it really draws upon their, frankly, immense experience running billions of containers a week internally. At its core, it automates the deployment, the management, and the scaling of all those containerized applications. You could think of it as the ultimate air traffic controller for your applications, maybe. It provides this unified, extensible framework to handle the complexities that are just inherent in distributed systems. It takes a huge amount of the operational burden off human teams.
I like that analogy, the air traffic controller. So when we talk about simplifying that potential chaos, what are the specific capabilities? What's Kubernetes actually bringing to the table?
Oh, it offers a really comprehensive suite of features. For instance, automated rollouts, scaling, and rollbacks. This means Kubernetes constantly monitors your containers. It automatically creates more replicas if demand surges. It distributes them across your infrastructure intelligently, and it reschedules them automatically if a machine goes down. All without you needing to step in once you've defined your desired state. It also handles things like service discovery, load balancing, and network ingress, basically ensuring your applications can find each other and that users can reliably access them from the outside. It supports both stateless and stateful applications. That's important means you can run persistent services like databases directly within Kubernetes now. And perhaps its most profound innovation is how it achieves all this through declarative state. You don't tell Kubernetes how to do something step by step. You just declare the outcome you want for your applications. I want 3 copies of this service running, for example. And Kubernetes continuously works behind the scenes to make that reality self-healing and adapting as needed. It's like telling a skilled gardener the kind of garden you want. And they just constantly tend to match your vision.
That declarative model sounds powerful. Now, when we talk about all this automation, all this speed, another term inevitably pops up alongside containers and Kubernetes. CI/CD. How does that whole automated pipeline concept fit into this modern software delivery ecosystem?
Right, the CI/CD pipeline, that's really the engine that drives the speed and the reliability we associate with modern software delivery. CI stands for continuous integration. This is where developers frequently merge their code changes back into a central repository, maybe multiple times a day, and that merge immediately triggers automated builds and, crucially, tests. The whole idea is to catch bugs and integration issues super early, ideally within minutes. Then CD stands for either continuous delivery or continuous deployment. Continuous delivery means your validated code is automatically released to, say, a staging environment, and it's always ready for immediate deployment to production with just a click. Continuous deployment takes it one step further. It pushes all the way to production automatically as long as all the automated tests pass. No human intervention needed for the final step.
So it's really that fully automated journey, from a developer committing new code all the way to that code potentially being live, serving users in production. What are the typical key stages or maybe checkpoints along that automated journey?
Yeah. A typical pipeline usually starts with the source stage. Any code commit, any change triggers the workflow. That moves into the build stage where the code is compiled into those runnable artifacts we talked about often, Docker images. Next comes the absolutely critical test stage. This runs a whole suite of automated checks: unit tests, integration tests, performance tests, security scans. Assuming everything passes, the deploy stage takes that thoroughly tested artifact and releases it. Could be to a dev environment, then staging, then finally production. And it often leverages Kubernetes, using tools to apply those manifest files and update the running application. And finally, there's usually a monitor and rollback stage. This continuously tracks the application's performance and health out in production. If issues arise, it can trigger immediate automatic rollbacks to a previous stable version.
It really sounds like an indispensable part of the whole picture now. Why is having a CI/CD pipeline so critical, especially when you're dealing with complex Kubernetes deployments?
Well, because trying to manage deployments manually in a Kubernetes environment, especially with potentially hundreds or thousands of moving parts, it would just lead to massive inefficiencies and errors, lots of errors. CI/CD pipelines enable faster deployments. They support those frequent releases maybe multiple times a day without disrupting ongoing operations. They allow for reliability with zero downtime. How? By integrating naturally with Kubernetes native deployment strategies like blue-green or canary deployments, which let you gradually shift traffic to new versions safely. And critically, they enhance quality and security. Because you embed automated testing and security scanning directly into the workflow, you catch problems way before they even get close to production. And for businesses, the benefits are just profound. You get faster time to market for new features. You see reduced costs and risks because you find and fix bugs early when they're cheap to fix. You get improved developer productivity. Developers aren't bogged down with manual deployment tasks. It fosters enhanced collaboration between dev and ops teams, DevOps, right? And ultimately, you get greater reliability and stability for your applications, which is what everyone wants.
So when we kind of knit all these pieces together, microservices, architecture, containerization, Kubernetes for orchestration, and CI/CD for automation, we're really talking about the core ideas behind cloud-native development. What does taking that fully integrated approach truly bring to the table for organizations? Why go through all this effort?
That's right. Cloud-native development, it's really about designing and building software systems that are scalable, resilient, and agile, specifically by fully leveraging the inherent principles and capabilities of cloud computing. It's building for the cloud. This integrated approach allows applications to adapt just seamlessly to changing workloads. It provides, real-time scalability and significant cost efficiency. Your applications can scale horizontally almost instantly to meet sudden demand, and then, just as importantly, contract again when demand drops, so you're only using and paying for the resources you actually need. And this also translates directly into greatly enhanced developer productivity, mainly through all that automation we discussed and the modularity that microservices enable. Smaller teams can work more independently.
Okay, but this incredible power, this flexibility,
Yeah.
it must come with its own set of complexities and challenges, surely. For companies that are embracing these cloud-native technologies, what are some of the biggest hurdles they typically face?
Oh, absolutely. While it's transformative, cloud-native development does introduce significant new challenges. One really critical area is simply managing the complexity of distributed systems. It's just harder. When you have potentially dozens or hundreds of microservices, each running in its own container, maybe spread across multiple Kubernetes clusters, just monitoring their health, debugging issues when they arise, ensuring overall reliability, it becomes far more intricate than dealing with a single traditional monolithic application. You just have so many more interconnected moving parts to worry about.
That absolutely makes sense. More components, more network calls, more potential points of failure. What about security? That seems like it would be a major concern in such a dynamic, distributed environment.
Security is, without a doubt, another paramount hurdle. The distributed nature of cloud-native systems, their reliance on APIs, shared components, ephemeral containers that come and go, it significantly increases the potential attack surface. There are just more doors and windows, so to speak. We often try to simplify thinking about security in these systems using something called the 4C security model: cloud, cluster, container, and code. Each C represents a critical layer where vulnerabilities can be introduced, and therefore where you need active defenses.
Interesting. Can you give us a quick rundown of what that looks like in practice? Say, for securing a typical Kubernetes environment using those 4Cs.
Sure. So at the cloud layer, that's about securing the underlying cloud infrastructure itself. Things like preventing unwanted access to the Kubernetes API server, the brain of the cluster, using robust authentication and authorization, making sure all connections use TLS encryption, auditing sensitive service accounts. Then, for the cluster layer, isolation is really key. You'll apply principles like least privilege using role-based access control or RBAC. That defines precisely who can do what within the cluster. You'll also use things like admission controllers, which act like gatekeepers, validating requests before they're allowed to make changes in the cluster. Next is the container layer. This focuses on things like only using verified scanned images, preferably from trusted private registries. And crucially is a big one, avoiding running containers as the root user whenever possible. This prevents privilege escalation if a container gets compromised. It's a simple best practice that can save you a world of pain. And finally, the code layer. This involves continuously scanning for vulnerabilities, not just in your own application code, but also in all the third-party libraries you depend on, which can be hundreds. And this is where that shift-left approach becomes vital. It means doing security testing as early as possible in the development lifecycle, ideally even before code is committed, not just bolting it on at the end. This comprehensive, multi-layered defense thinking about cloud, cluster, container, and code is absolutely essential.
Right. But even with all those best practices meticulously in place, the reality of any complex system, especially distributed ones, is that things will eventually go wrong. Something will break. What does it actually look like to troubleshoot issues in a modern Kubernetes environment? Is it really like searching for that needle in a haystack sometimes?
Yeah. Troubleshooting Kubernetes can definitely feel like that sometimes. It is complex. Maybe think of it less like fixing a simple machine and more like being a detective in a huge, bustling city with a million interconnected streets and systems. You can't just look for one broken window. You have to understand the entire ecosystem, how all those services, pods, nodes, network resources interact. The key pillars for effective troubleshooting, I'd say, are first, really understanding the issue, what's actually happening. Then managing it, diagnosing the root cause and fixing it, and finally, preventing it from happening again.
And what are some of the most common issues, the typical symptoms you might encounter when something does go sideways in Kubernetes?
Oh, you'll frequently see things like containers or pods just failing to start, or applications responding really slowly, or maybe unexpected crashes. Common error messages you might investigate include things like crash loop backoff. That basically means a container is starting, crashing, restarting, crashing again in a loop. It can't stay up. Or you might see own killed, which stands for out of memory killed. That means a container was forcibly shut down by Kubernetes because it tried to use more memory than it was allocated. The real challenge, though, isn't just seeing these symptoms, it's tracing them back to the actual root cause. That could be anything from a misconfigured network policy blocking communication to a subtle bug in your application code that only shows up under load, or maybe just insufficient CPU or memory resources allocated to that particular container. It really demands a systematic approach. You have to clearly define the problem's scope, meticulously look for error codes and logs from various places, and leverage metrics from your monitoring systems, Prometheus, Grafana, tools like that. It's often less about finding one single smoking gun and more about piecing together subtle clues from multiple sources across the system.
So considering everything we've covered today, the evolution, the tools, the complexities, the troubleshooting, what's the key takeaway? What does this all mean for someone navigating this incredibly dynamic and, frankly, rapidly evolving landscape of cloud-native development?
I think it means that while these incredibly powerful tools and automated systems provide capabilities we could only dream of a decade ago, well, continuous learning and constant vigilance are absolutely paramount. They're not optional. The very nature of cloud-native development is one of constant evolution. New tools, new patterns, new challenges emerge all the time. It demands adaptability from individuals and teams and a really deep understanding of how all these interconnected pieces, the containers, Kubernetes, the CI/CD pipelines, the underlying cloud infrastructure, the security posture, how they all interact and influence each other. It's definitely a journey, not some fixed destination you arrive at.
That's a great way to put it. This deep dive into containers, Kubernetes, and CI/CD pipelines really does highlight just how far we've come in software delivery. It truly is a world built on speed, flexibility, and automation now.
And it's a world that absolutely demands robust, resilient, and secure underlying infrastructure to actually support all that rapid innovation. The faster you build your house, the more critical the foundation becomes.
Exactly right. Because no matter how agile your application deployment process is, no matter how quickly you can spin things up and down, the bedrock of any application is ultimately its data. That data needs to be accessible when needed, it needs to be protected from loss or corruption, and it absolutely needs to be secure from threats. So as we all navigate this ever-evolving landscape where applications are built and deployed with just unprecedented speed and scale, perhaps the ultimate deep dive isn't just into the technology itself, but maybe into our own capacity for continuous adaptation and ensuring that the very foundation upon which these digital worlds are built is truly unshakable. And on that note, a big thank you once again to our sponsor, Stonefly. Quick mention, did you know Stonefly offers a 100 TB immutable and air-gapped SSO NAS for just $8,995? It's designed specifically to provide those robust, secure storage solutions that are so critical for today's dynamic, cloud-native environments, ensuring your valuable data is protected and always available, even against sophisticated threats like ransomware. You can check out stonefly.com for more information on that and their other solutions.
Well, that's all for this deep dive. We really hope you feel a little more well-informed and maybe ready to explore these fascinating topics even further on your own. Join us next time for another deep dive.